Hello everyone, welcome back to Bamane Pharm Lectures, where we make pharmacy simple for you. In today's lecture, we are going to learn how we can convert from milliequivalents to grams or milligrams, or the reverse, from milligrams or grams to milliequivalents. This is the most confusing part when it comes to calculations involving milliequivalents. Students often find challenges on how they can interconvert between those units. Today, if you have been wondering and confused about how you can go about such questions, this is your lecture. Just pay a very keen attention, and please, if this is your first time to watch or learn with us, please subscribe to the channel, like it and share it with other people who may also find it very useful. My name is Bamane, and I am a tutor, and I am here help you excel in your exams and pharmaceutical lab practice. So, before us is the question: calculate the amount of salts required for the following. They have provided us the ions and the molecular weight of each of these ions. So, every time we are required to convert from milliequivalents to grams, remember, milliequivalents are not weighable quantities. So we have to labor at all times to convert them into weighable quantities of mass. And we often get these questions in lab practicals where you provide these quantities in milligrams and they want you to write a label. And remember, the labels for injectables must always be written in milliequivalents or millimoles. So today we are going to look at all that, and by the end of this lecture you will be able to convert any question involving milliequivalents or millimoles that requires you to convert them into weighable quantities of mass like grams and milligrams. Let's get started. So the first thing we need to know, we need to get the mass amount of sodium chloride. Remember, we cannot weigh ions, but we weigh their salts. So, what do we know? They have given us the molecular weight, the milliequivalent in 1,000 of sodium ion. And they have also given us the molecular weight as 58.5. But what do we know? Remember, we need to ascertain the relationship between the molecular weight we have and the milliequivalent, which is given in the formula. So what happened is, we said that equivalent weight is ratio of molecular weight divided by values of the ion. So, the first thing always, if you're converting from milligrams to milliequivalents to grams, is to first of all ascertain the equivalent weight of that compound, then go further and obtain the milliequivalent in one, the amount of sodium chloride in 1 milliequivalent. So, after knowing this, we know that molecular weight of sodium chloride as 58.5, and we know sodium has got 1 ion. So that means we shall have 58.5 grams as the equivalent weight for sodium chloride. But remember, from our definition of milliequivalent, we say that 1 milliequivalent is equal to 1 out of 1,000 times equivalent weight. Because we say that milliequivalent is the amount in milligrams of a solute that is equal to 1,000th part of its gram equivalent weight. So 1 milliequivalent of sodium chloride will be equal to 1 out of 1,000 times equivalent weight, which is 58.5. So this will give us 0.0585 grams. But remember, we said it should be in grams. But remember, 1 gram is equal to 1,000 milligrams. So we shall simply multiply this by 1,000 so that we can have 58.5 milligrams of sodium chloride. So if 1 milliequivalent is equal or is contained in 58.5 milligrams, how about the required in the formula? So we shall say from first principle that 1 milliequivalent is contained in 58.5 milligrams of sodium chloride. How about the 20 milliequivalent? This will be contained in 58.5 divided by 1 times the 20. And when we compute this, we are going to get 58.5 times 20. We shall have 1,170 milligrams, which is also the same as 1.2 grams if we can convert to grams and approx round off. So this is the mass of sodium chloride, which is equivalent to the 20 milliequivalents in the formula. So how about for potassium chloride? So for potassium chloride, we know the molecular weight of potassium chloride. But remember, we have said that 1 milliequivalent is equal to 1 out of 1,000 times equivalent weight. So that means since potassium has got 1 valence, we know that its equivalent weight will be equal to its molecular weight divided by 5.5 divided by 1, which will also still give us the same answer as 1 out of 1,000 times 74.5. So when we convert this, we shall get 0.0745 grams. But remember, we said it should be in milligrams. So this will be 74.5 milligrams of potassium chloride. That is the amount of potassium chloride which is equivalent to 1 milliequivalent. So we are going to say if 1 milliequivalent of potassium chloride is contained in 74.5 milligrams, how about the one given in the formula? So the 30 milliequivalent will contain 74.5 divided by 1 times 30. And when we compute that, you realize that we are going to get 2,235 milligrams. And when we convert this to grams, we shall have 2.2 grams. It is simply we just divide by 1,000. So this is the mass of potassium chloride in 30 milligrams of the formula. How about now the magnesium chloride? So magnesium chloride, it is going to be, now we know that equivalent weight of magnesium chloride, those 6 water of crystallization they have already given us, this will be equal to the molecular weight, which is 203. But remember, magnesium has got a valence of 2. So we are going to divide this by 2, and when we divide, we shall get 101.5 grams. So, but remember, 1 milliequivalent is equal to 1 out of 1,000 times the equivalent weight, which is 101.5. And when we compute this, we are going to get 0.1015 grams. And when we convert this back into milligrams, we simply just multiply by 1000. So we shall have 101.5 milligrams. So we have gotten the equivalence of 1 milliequivalent. So we shall say if 1 milliequivalent of magnesium ion is contained in 101.5 milligrams of magnesium chloride, how about the 5 milliequivalents in the formula? It will be 101.5 divided by 1 times 5. And when we compute that, 101.5 times the 5, we shall get 507.5 milliequivalent. And when we divide this by 1000, we shall get approximately 0.5 grams of magnesium chloride. So what does that mean? That means that our final product formula, what we sometimes call the working formula, is going to be sodium chloride, which we have obtained as 1.2 grams. We shall have potassium chloride, which we have obtained as 2.2 grams. We shall also have magnesium chloride, which we have also obtained from our question as 0.5. Then water for injection, add to 1000 mils, and that becomes our final product formula for this question. And that's how we can convert from milliequivalents to milligrams or grams. Let's look at our second example. And if you have not got me well here, please pay attention in our next example. Let's look at our second example. You can feel free to pause this video and see if you can get the same answer with me. Calculate the weight of salts required for the following. They have given us the ions. So we are going to begin by calculating. But before, there is one unique thing in this question. They have given us sodium chloride, but we also need to have, so we have sodium chloride and we also have disodium hydrogen phosphate. So that means this amount of sodium ion is going to be divided between the disodium hydrogen phosphate and the chloride ion in this case. So, but what determines that, you look at the number of milliequivalents that we have for the phosphate ion. So, since this one is 8, it means that for disodium hydrogen phosphate is having 8 milliequivalents. So that means the remaining will be for the sodium ion. So 8 milliequivalent is for sodium, which is combining with the hydrogen phosphate, and the balance will be for the chloride. So in this case, we are going to have sodium as 10 milliequivalent, because already the 8 has gone with the phosphate ion. So it means for sodium chloride, we are going to say if 1 milliequivalent of sodium, each of sodium ion and chloride is contained in 58.5 milligrams. I think when I simply just write the 58.5 milligrams, you can now get to know where I am getting it. Because we have said that equivalent weight of sodium chloride will be 58.5 divided by 1. So if we get what is in 1 milliequivalent, it will be 1 out of 1000 times the equivalent weight, which is 58.5, and this will give you 0.0585. And when we convert this to milligram, we simply just multiply it with 1000. So this will be 58.5 milligrams. That's why I am saying 1 milliequivalent each of sodium and chloride ion is contained in 58.5 milligrams. So every time you have an ion which is having a valence of 1, the molecular weight is always equal to the equivalent weight. So how about the 10 milliequivalents? This will be equal to 58.5 divided by 1 times 10. So when you multiply this by 10, you realize that the 10 is going to remove the decimal point, and we shall have 585 milligrams. If you want to convert it to grams, then we shall simply divide by 1000, which will give us 0.585 grams as our answer in this case. So we shall go to now potassium chloride. With potassium chloride, we know it has a molecular weight of 74.5. But remember, potassium has got 1 value. So it means that 1 milliequivalent still, each of potassium and chloride ion is contained in 74.5 milligrams. How about the one given in the formula, which is 15 milliequivalents? This will be equal to 74.5 times 15 divided by 1. When you compute this, we shall have 74.5 times 15, we shall get 1117.5 milligrams, which if you convert it to grams, you simply just divide by 1000, and we shall get 1.117.1175 grams. So this is the mass of potassium chloride, which is equivalent to the 15 milliequivalents. So our next thing here is going to be now the disodium hydrogen phosphate. So what happens to this? We shall also get its equivalent weight. But remember, sodium here has got 1 valence. So we shall still have 268 divided by 1 to get its equivalent weight, which will still be the same. So that means when we divide this by 1000, we shall get what is in 1 milliequivalent. So I would say if 1 milliequivalent each of sodium and phosphate ion is contained in 268 milligrams. How about the one in the formula? So the 8 milliequivalent will be contained in 268 times 8 divided by 1. And when we compute this, 268 times 8, we shall get 2144 milligrams. And when you convert this to grams, we shall simply divide by 1000, and we shall get 2.144 grams. So you realize that we have gotten the mass of each of the ingredients in the formula. So that means if we are writing our final product formula or working formula, it is going to be sodium chloride, potassium chloride, and then dihydrogen phosphate. whereby we got sodium chloride as 585 milligrams. We got potassium chloride as 1117.5 milligrams. We got for disodium hydrogen phosphate as 2144 milligrams. So these are the quantities we needed to, which represents the solids that have got these mole equivalents. I hope you have got me. In case you still have any doubt about any question, please ask in the comment section. I will be happy to help you. Let's look at our third example. So, our third example, they are telling us express 0.9% sodium chloride in milliequivalents per liter. So, the guiding word here is per liter. And we need to know what does 0.9% sodium chloride means. From our knowledge of the dilution, we said when we say 0.9%, we simply mean we have 0.9 grams of sodium chloride in 100 mils of the solution. So, we need also to ascertain if this mass is in one angle, how about the southern of the question? So, this will be 100 mils of the solution containing 0.9 grams of sodium chloride. How about the 1000 mils? It will contain 0.9 divided by 100 times 1000. And when you compute this, we shall get 9 grams per liter of sodium chloride. So if we get 9 grams per liter of sodium chloride, our main aim is to convert it into milliequivalents per liter. But remember, we know that the molar mass or molecular weight of sodium chloride is 58.5 grams per mole. So we are going to get the equivalent weight of sodium chloride, which we know that equivalent weight of sodium chloride is equal to its molecular weight divided by valence, which is 1, and we shall still get 58.5. But our main aim, we want to get the milliequivalents. So, but remember we said 1 milliequivalent of sodium chloride will be equal to 1 out of 1000 from the definition of milliequivalent times the equivalent weight, but the answer should be in milligrams. So this will be 0.0585 grams. But when you multiply this by 1000, we shall get 58.5 milligrams. So if 1 milliequivalent of sodium chloride is contained in 58.5 milligrams, how about the weight being given in this case? So we are simply going to alter, since what we want is milliequivalent, we are going to say that 58.5 milligrams of sodium chloride contains 1 milliequivalent per liter. How about the 9 grams, which can be 9,000 milligrams, because the units has to match. We can multiply this by 1000 converted to milligrams. So this will be 1 out of 58.5 times 9,000. And when we compute this, we shall have 9,000 divided by 58.5, which gives us 153.8 milliequivalent per liter, which is approximately 154 milliequivalent per liter. So this is the number of milliequivalents per liter in 0.9% sodium chloride. Let's look at our first example. So our first example, calculate the weight of the following salts required for the following. They have given us sodium chloride 20, calcium chloride 30, magnesium chloride 5, phosphate iron 10, chloride iron 10, they don't have to add up to 1,000. This will be your official assignment. Feel free to pick up your calculator and the pen and solve it out and comment with your answer in the comment section. And where you don't get well, please raise your concern in the comment section. I'll be right by to help you. And if you find this video very useful, please like, subscribe to my channel to keep you updated with more simplified pharmacy videos. And also don't forget to share the channel in your various class groups or with other colleagues who may also find it very useful. Let's catch up in the next lecture, and don't forget, in our next lecture we shall be looking at how we can use mean equivalents adjust to isotonicity. Let's catch up.